So my name is Shubham Rai, and I am a PhD research scholar in Department of Applied Mechanics, IIT Delhi. So today we will be continuing with week 9. So this is a live interactive session corresponding to the lectures which have been covered in NPTEL during week 9. So let me start. So this is week 9. Okay. So in week 9, you would have studied related to pure bending of rectangular beams. So let me just set this camera. Okay. So you would have studied related to pure bending of rectangular beams. First topic that was covered was pure bending of rectangular beams. Then you would have studied related to bending of beams where you have variable bending moment. So bending moment is varying with the length of the beam, let's say. So you would have studied bending of beams. And then you would have studied bending of unsymmetrical beams. Okay. So let me just write down the formulas that were there in the lectures, then we will continue with the questions. So in case of pure bending, so you have, what was the formula for longitudinal strain in case of pure bending? Can someone tell me what was the expression for longitudinal strain in case of pure bending? So let me first draw the diagram of beam. So this kind of curvature. And let's say this is the center of the beam, center of radius of curvature. Right? So and this is the neutral axis. So this is the radius. I mean, this is pure bending, so it will be completely circular. Neutral axis will bend in a circular manner, and this will be the radius of that circle. And I'm saying that let's say the cross section of the beam is kind of rectangular, and let's say the cross section is rectangular. The beam has this kind of cross section. So this will be the neutral axis. I'm just writing it as any. Okay, and this is any point which is at a distance of y from the neutral axis. This point is y. And so we say that this r is the radius of curvature, and this inverse of r, a reciprocal of r, is known as curvature, which is denoted by kappa. Like this. So it is known as curvature. It is reciprocal of radius. So the coordinate system that we are following is along the axis of the beam, we have x-axis, right? And perpendicular to x-axis in the same plane, we have y-axis, which is along the thickness of the beam. And along the width of the beam, we have z-axis. So this will be the convention that we will be following. Okay. And this cross section here. So can you tell me in which plane this cross section will be? So this cross section will be in YZ plane. So this is YZ plane, right? Because you are um, looking along the x-axis. So you will see this cross section. So now the expression for longitudinal strain, if you remember, so that will be epsilon xx, and this is minus y by radius curvature. Or you can also write minus y times kappa, because kappa is 1 by r. Okay. Similarly, what will be the longitudinal stress? So you just have to use constitutive relation. And this material is, we are assuming that it is a linear elastic material and isotropic also. So linear elastic isotropic material. So longitudinal stress. So we will have longitudinal stress as sigma xx, which will be equal to E times epsilon xx, which is equal to minus of E into y by r. Right? These are fairly simple formulas, or these are very simple to derive as well. You can go back to lectures to see their derivation. I'm just writing the formulas. Now, let's say I want to write this radius of curvature, expression for this radius of curvature. So, what do you think? On which quantities this radius of curvature is going to depend on? Please tell me. So, let's say I'm applying a bending moment at the end points of this beam. So, as I increase the bending moment, what will happen to the radius of curvature? Will it increase or decrease? Yeah, so it will decrease because beam beam will be bent more, and since bend there will be more bending, the radius of curvature will decrease. And what will happen to the radius of curvature if the second moment of area of beam is high? So if second moment is high, so it will be difficult to bend the beam. So the radius of curvature will increase. So we can say that radius of curvature is directly proportional to second moment of area, inversely proportional to applied um, bending moment. And then what about modulus of the material? So if Young's modulus of the material will be high, it will be difficult to bend the beam. Okay, because for the same stress there will be less strain. That's the meaning of more Young's modulus of elasticity. So the stiffness of the material will increase, so bending will be difficult, so radius of curvature will still be high. So it will be directly proportional to the modulus of the material as well. So obviously now we have the formula. So formula for this is, I mean, this is a qualitative argument, and the formula can be derived exactly. The expression can be derived in a mathematical way. So the expression is into I ZZ over moment about the axis. And this will be the formula of radius of curvature. Now, um, so you can also write the applied moment. So now if you want to calculate applied moment from this, let's say radius of curvature is given and you want to calculate applied moment, so it will be EI by R, right? Or you can say that it will be E into I ZZ times kappa. Now you can also write strain again, epsilon xx. So that was minus of E into, yeah, so let me write stress, okay? The stress was, what was stress? Stress was minus of E into Y by R, right? So um, from here, E by R is equal to M by I. So you can substitute here. So E by R will be M by I. So it will be minus of M Y by E. Sorry, M Y by I. So we'll get MZZ or MZ, is writing Y divided by IZZ. Right? So this is the expression of stress. And this is also known as bending equation. It- And of course, now let's say you want to calculate IZZ, that is second moment of area for any given cross section. So let's say the cross section is rectangular. So let's say the cross section is rectangular, and then this is the neutral axis. And you want to calculate IZZ about this axis. So expression of second moment of area is underscore y square dA, and y will be the distance from neutral axis. Actually, it will be the distance from centroidal axis. Uh, but here we are assuming that neutral axis is coinciding with centroidal axis. So, I mean, we are not assuming it will coincide because it is the case of symmetrical bending. So now, let's say this distance here is y, and the neutral axis is y, and dA will be small area element. So let's say this is dA here. Here we have dA, a small area element, and so its width will be dy. So this will be dy. And you can say length is dy, and width will be this width. So this will be dz because we are in yz plane. This is z, this is y. Okay. So, and let's say the total height of this rectangular cross-section is h, and width is b. Right. So you will get finally y square dA is dy dz, right? So that will be area, this small element, and you integrate from here to do double integration because you are integrating respect to area here. So z will go from minus h by 2 to h by 2. Sorry, y will go from minus h by 2 to h by 2. So let me just and z will go from so z will go from 0 to b. Or sorry, it will minus b by 2 to b by 2 because we are taking our actually our x is at the center. Okay, so we are taking this coordinate system at the center of the cross section. So that's why it's like this. Now, if you calculate, so what will be the formula? So y square di will be y cube by 3. And this will go from minus a square root by square root. and still you have minus b by 2 dv by 2 dz, right? So to calculate, this will be h cube by 8 multiplied by 6, h cube by 24, and then 2 times because this minus h by 2 will be plus if you solve it. So it will be 2 times h cube by 24, so it will be h cube by 12. So h cube by 12 will come outside integration, and then you have minus b by 2, b by 2 and dz. So if integration of dz will be z, and if you apply the upper and lower bounds, you will get minus, you will get b by 2 and plus b by 2. So it will be b. So finally you will get 1 by 12 b squared. So this is the second moment of area of a rectangular cross section. And just for the sake of memorizing this formula or using it fastly in the questions, you can just see that this h cube. So the dimension which has cube over it is the dimension uh, which is intersected by this neutral axis. So this dimension b is parallel to neutral axis, but this dimension h is intersected by this neutral axis. So the dimension which has been intersected, there will be cube over that dimension. Okay, so you can remember in this code just for the rectangular cross sections. And by that, I'm not promoting memorizing, but yeah, sometimes just to solve questions fastly. Each time you cannot derive this formula and you understand. Although derivation is simple, but then now let's try to find out the expression for epsilon y y. Epsilon xx, we have constraint in y direction that we need to find out. Epsilon xx we have already found out. So epsilon xx was this minus y by r. Now epsilon y y, that will be 1 over e sigma y y minus mu into sigma xx plus sigma z y. Right? Now sigma y y and sigma z z are 0 because there are no stretches in both direction. We are only applying bending moment. So expression for so these are 0, so we will have minus of mu y into sigma xx. Because sigma y y will be 0 and sigma z z will also be 0. So you can just put the expression for sigma xx that we have and put that. So you get mu into y by r because sigma xx is e into minus e into y by r. So finally you have this epsilon y by which is equal to mu into y by r. And this is also equal to epsilon z z. Moving ahead. So this was all related to pure bending. Now moving on to the bending, where pure bending moment can vary across the length of the beam. So this right. In case of bending of beams, so in case of bending of beams, you have sigma xx. So that will be a function of xyz. let's say that will be given by minus mx. M now is a function of x into y by I z z. So sigma xx will now be a function of x also. Earlier it was not a function of x because m was not a function of x. Okay. Sigma xx will be a function of x now. I mean, it will vary across the length of the beam. Now you have, so let me just write it. So this is variation of normal stress. And then you have rho xy as well, which is again a function of x, y, x and y. So the expression for this is Vx times 2y divided by Izz to Vy. So you have here you have variation one shear stress due to bending of beams. So V of x is shear force. V of y is let me just draw a diagram. Let's say this is the cross section of the beam, and here you have neutral axis, and this is the shaded region. Let's say this is at the shaded region is at a point y from the neutral axis, and this is the centroid of this shaded region. Okay, so V of x is shear force that will be acting on this cross section, and V of y is width of this shaded region, width of the shaded region, and U of y is first moment, first moment of area of shaded region, first moment of area of shaded region, right? Now you can also write it as area of shaded region times the y coordinate of the centroid of the shaded region. So this is known as flow. So y coordinate of centroid of the shaded region will be this way. Here you have y1. Okay. Now let me write some formulas for shear stress distribution in thin and open sections. So that was related to unsymmetrical bending. Let me just quickly write that. right? So firstly, let me draw the diagram of chain and open cross section. So let's say you have cross section like this. Okay. So let's say S is moving along the curve of this cross section. S is the coordinate along the curve of the cross section, and say you are at origin. So this is Z axis, and this is Y axis, right? And mean will be perpendicular to this YZ plane. So when we write tau Sx, right? So Sx means um, this is the x plane. So this normal of this plane will be in x direction, right? And S is the direction of shear stress. So this is plane normal. I can say that this is representing plane, and this is representing direction. And this will be a function of both x and s. Now let me just write the formula for tau Sx. That will be minus of 1 over thickness Ts and I y z square. So these are second moment of area. I y z square minus I y y times I z z. This is, and then this is multiplied by this quantity here, minus Vy and Qys Iyy minus Qzs. So Q I already defined above. Qzs Iyz plus Vz Qy s Iyz minus Uzs Izz. Okay. So, and if y and z are along principal axis, so the formula yz will be Iyz will be 0. So if y and z are along principal axis of the cross section, so Iyz will be 0. Therefore, it's right. So in this case, we say that Iyz will be 0. That is, it vanishes. So the formula will reduce to tau Sx will be 1 over. Just put Iyz equal to 0. So you will get this as this is minus, already minus is there. So 1 over Iyy Izz times Ts, right? And in the bracket, what will be left? So this term will go to 0, this term will go to 0. So you will only be left with two terms, right? So this will be minus of Qys Iyy and minus of Qzs Izz, and this will be multiplied with Vy, and this will be multiplied with Vz. So finally, you will get minus of Vi minus of Vy Qys times Iyy minus Vz Qzs and Izz. This will be the formula. Now further, if you will simplify, so you will get minus of Vy Qys over Izz into Ts minus of Vz into Qzs over Iyy into Ts. So that is all related to formulas. So let me write down few problems. Problem one. It says for an I section beam, assume the beam is subjected to transverse load. First, what you have to obtain, we have to first obtain an expression for variation in shear stress to xy within its cross section. And I'll draw the diagram of I section, don't worry about it. The first part, you have to find expression for variation in shear stress. In the second part, you have to find using the expression above, I mean using the expression found in part A, we have to draw a graph which will depict depicting qualitative variation. You only have to give qualitative variation, not quantitative. Qualitative variation in shear stress within the cross section. Okay. In part C, we will solve where is this shear stress maximum. So from this expression, you will be able to see From this qualitative analysis, you will be able to see where is the shear stress maximum, and you have to find the ratio of maximum shear stress to average shear stress. In the cross section. So this is the question. Let me draw the I section. So I section looks something like this. Okay, so this is the I section, and the dimensions are, so this dimension is T, this is also T, and this width of upper and lower flanges are equal. So this width is B, and let's say this is the neutral axis. That will coincide with the centroid of the symmetry because it is symmetrical across, symmetrical about the neutral axis. So let's say this length is L, and this length is also L. So this part here, this part here is known as flange, and this is known as web. So in first part, what we need to find out your total expression for variation in shear stress tau xy within its cross section. So expression for tau xy you already know. Tau xy, so this is the solution. Tau xy, which is a function of x comma y, that it will be Vx Qy over Izz times, let me just, or By. So here B is constant, it's not a function of y. So anyway, in this expression we do not know Qy and we do not know Izz. So let me just, in this expression we do not know what is Qy, and we do not know what is Izz. So these two things we do not know. And shear force, I'm assuming that on a particular cross section we know the shear force that you can find once you have been given some bending moment, or the force which is acting on the beam. So let's calculate firstly the second moment of area. So I, Z, Z. So how will you do that? So if you see here, second moment of area will be second moment of area of this. So we can take a centroidal axis. So let's say this axis is, let me store. Let's say this axis is at the center of the flange, and this axis is x1, right? So this is at the center of the flange. So and um, let's calculate IZZ. So firstly, I'm calculating IZZ for flange, and then I'll calculate IZZ for full web, and then add both of them. So IZZ for flange about this neutral axis will be, let me just write IZZ for this T. I'm writing this T means flange. So that will be what will be IZZ about this neutral axis. So if we find the IZZ of this flange about this axis, which is the centroidal axis of the flange, and then we apply parallel axis theorem, and we transport this from here to this about to this axis. So parallel axis theorem says that IZZ flange about neutral axis will be IZZ flange about x1 axis, is centroidal axis of the flange, plus area of the flange times y bar square. Y bar is centroid of the flange. Y coordinate of the centroid of the flange from the neutral axis. So that will be this distance here. This distance. This will mostly be y. Okay. And here centroidal axis and neutral axis are coinciding. So anyway. So this is parallel axis theorem. So we just find out. So IZZ for this flange about x1 axis will be, so this is T, this is B, and this axis is intersecting this dimension T. So it will be 1 by 12 B into T cube. And then there are two flanges, so it will be twice of that. So let me just write it down. So this will be, let me first write down for one flange. So it will be 1 by 12 BT cube plus area of the flange will be B times T, and centroid distance of centroid of the flange from neutral axis will be L plus this distance is L, and plus this distance which is T by 2. So L plus T by 2. Right? And whole square of that obviously. So this is IZZ for one flange. Okay, now let's find out IZZ for web. For web I'm writing W for full web. So it's very easy because about this neutral axis, this web is a rectangle. So it will be 1 by 12, 2L to the whole cube times this. And this is also T actually, not written, but this is T. Thickness of the plant is also T. So, so this will be simple. So it will be 1 by 12 thickness times 2L to the whole cube. So you will get how much? 8 TL cube by 12. Right. Now, similarly, let's say you have IZZ, so it will be twice of IZZ plus IZZ of flange because there are two flanges. So this is about neutral axis. That's why I've written IZZ. And I've not mentioned anything means it is about neutral axis only. So twice of IZZ flange plus IZZ of web. So what will you get? So you will get 2 by 12 BTQ plus 2BT L plus T by 2 the whole square plus 8 PL cube by 12. And you can further simplify it. But this is the final expression for IZZ. Okay. Okay, so let me. So we have calculated second moment of area. Now we have to calculate QY. So for calculating QY, how can you do it? So it is QY is first moment of area. So you have to calculate Y into dA and integrate it over the cross section. How will you do that? So let's firstly calculate QY for the flange. So let's first consider the flange. Okay. The writing has if we consider the flange, so QI for the flange, how will you calculate? So YDA, so actually it is integration of YDA. So we can also write it as Y bar into A. So Y bar we already know, and it is of the shaded region. So let's say we are at this will be function of Y. So let's say we are at particular Y. So this is the function of Y, actually. Let's say we are at this particular Y. Let me just know that. Let's say we are at this particular Y, okay? And so we need to find out Y bar into A for this scheduled region, right? So there are two things. One part is this web and one part is this flange. So for this flange, Y bar into A will be since this is the whole flange, so this will be Y coordinate from from this point. Um, Let me just see. Q will be a function of Y. Okay. For the flange, it will be YDA. Yes. This you can write as B into B is the width of the flange, and so this is L. So this distance of the centroid will be let me just first find out. So this distance will be L minus Y, and this distance is T. Okay. Yeah. So V into G plus L minus Y. When we are considering four plants, so we cannot take this axis, we'll have to take some y axis in the flange. We can draw firstly a y axis in the flange. So let's say we are at any point here. Let's say we are here and this point is at distance y. So we have this as the shaded region now when we are in the flange. So for this shaded region, we have to find Q. Q will be area times centroid of this shaded region. Area of the shaded region will be, so this whole distance is L plus T. So this distance left is um, L plus T minus Y. So we can say that this distance here, so this distance I'm just writing here. So it will be L plus T minus Y from the neutral axis, right? And so area of this shaded region will be the sky blue shaded region. This will be width times this thickness. So width B times L plus T minus Y, and then multiplied with the centroid. Centroid will be here, somewhere here. So that will be this Y plus this thickness divided by 2, right? So it will be, let's say, somewhere here. So let me just write what I have discussed now. So it will be B times thickness of that sky blue shaded region. So that is L plus T minus Y. And then multiplied by centroid. Centroid will be Y plus L plus T minus Y by 2. Thickness divided by 2, right? So if you solve this, you will get B by 2. And I'm just writing here as T plus L minus Y. And here you will get T plus L plus Y. So this will be the Qi for the flange. And once you have Qi for the flange, so what we are going to do is we are going to write distribution of uh, transverse shear stress separately for the flange and for the web. So since now we have Qi for the flange, you can write to Yx for the flange. So Yx for the flange is transverse shear force multiplied by Qi. Qi is nothing but V by 2. And if you solve this, it is nothing but A plus B, A minus B. So it will be T plus L to the whole square minus Y square. So you have T plus L to the whole square minus Y square and divided by Ixx into B. Sorry, Izz into B. So you have Izz into B. So this is the expression. So Izz will not be a function of Y. So that's why I've written Izz only here, right? And which you have already calculated above. And then this is also not function of Y. This is also constant force, shear force at particular cross section. So the expression of Y we have written here. So tau ix will vary with y as per this expression. Now let's find it out for the web. So qy for the web, we'll have to take now y coordinate of the web. So let me, so for the plan we have done, right? For the web, let me choose some different color. Let's say you have, let's choose a yellow color, and let's say you have y here. So let's say you have y here. So the shaded region will be this total region up to here. This flange plus web, because you are, because transverse shear stress will have effect of the section above as well. So we'll consider uh, web plus flange here in this case. Now, I mean, this will be this complete region web plus flange. So this extra region, yellow region will be there. So we'll have to find Q. So for Q, and this is first moment of area. So that is centroid of the shaded region times area of the shaded region. So I can find it out separately for the flange and for the web. So if I consider the flange, so area of the flange is B into T now. And from the neutral axis, the centroid of the flange will be at this L plus T by 2, because centroid of the flange will be now at here, because now we are considering this full flange, because we have to consider this full shaded area, and in this shaded area now, the flange, full flange has been covered, because we have gone up to web. So that's why this area of the flange will be B into T, and centroid of the flange will be L plus T by 2. So let me write that. So this will be B into T times L plus T by 2. Now coming on to the web plus. So for the web, what will be the area of the web? So area of the web will be this length now is L minus Y, right? L minus Y. So area of the web will be T into L minus Y. So let me just write that. This is area. And what will be the centroid of this web portion? So it will be somewhere here at the center. Let's say here. So this will be nothing but this distance from this Y will be L minus Y by 2, because it will be at half of the thickness. So net distance from the neutral axis will be Y plus L minus Y by 2. So let me just write it down here. So it will be, okay. So this is the overall expression of Qy for the web. So let me simplify this expression. So this is T by 2. And to solve this, you will get here L plus Y. So L plus Y into L minus Y will be L square minus Y square. So I'm just writing. So this is the final expression of Qi. And now you have tau Yx. So that will be Vx times Qi, which is Vt into L plus T by 2 plus T by 2 into L square minus Y square, right? And then divided by Ixx into width. So I z z into width is here t. Width of the flange is t. So you have this expression. I think we have completed part A of this question. Now you try to solve part B. In part B, using the expression. So now you have expression for the yx for the flange and for the web. So you try to plot that, and it will be symmetrical about neutral axis. So you can just copy the pattern which is above the neutral axis to below the neutral axis as well. So yeah, please try to do that. I'll be back in a minute. Yes, so I hope you would have done something. So let me just draw variation of tau yx. So let's say here I have y axis, and here on the x axis I will plot tau xy, tau yx. So let me put, let me firstly draw, then I will draw. So here I'm drawing the flange, and flange and the web. So Third is this one. Fourth is this one. Let's say these are parallel lines. And if we plot the variation, so again, let me just write. So this is T, and this is L, and this is L, and this is T. Now, if we plot the variation, so what will happen? So let me start from, so let's say, and this will be neutral axis, of course. This will be neutral axis. We have to plot a qualitative trend. So at y is equal to L plus T. So if you put y is equal to L plus T, this will be 0. So we'll start from 0 because this point is y is equal to L plus T. Here this we have y. So we start from 0 and it will be parabolic variation. So we'll go something like this. So it's a quadratic variation. So we'll go something like this. Okay. And then on the flange, it will suddenly increase. And then again, but it is increasing because area of the flange is less. Okay. So it will increase. Um, and then because we are assuming that 2L into B is less than B into T. 2L into T is less than B into T. I mean, it is increasing because see this area, this width is smaller compared to flange. You can see from actually this formula that this extra term is there here, right? So if you put y is equal to L, this term will vanish and you will be left with Bt into L plus T value and this, right? And if you put y is equal to L here, so what will happen? You will get a quantity smaller than this term. You can try. And that is because the denominator here you have T and here you have B. So B is large compared to T. That will also make difference. Anyway, you can find the exact values. I'm just plotting a trend. And you can find the exact values and plot, but the trend will be same. So this will be the trend. It will increase suddenly in the flange because thickness of the, I mean, width of the flange is less. Okay. And other geometrical, it depends on other geometrical parameters also. You can just rely on this formula. If you try and find out, there will be jump here in this tau yx. So this is the variation of tau yx. And as you are able to see, it is maximum on the neutral axis. So in part C, it has been asked that you have to find maximum where it will be maximum. So we say that shear stress is maximum at the neutral axis. Shear stress is maximum at the neutral axis. And also you have to find the ratio of maximum shear stress to the average shear stress. So average shear stress you can find by this expression. Maximum shear stress you can find. So this that will be in flange. So you can flange if you put y is equal to 0. So you put y is equal to 0 here. So you will get maximum expression for maximum shear stress. And I'm just writing the expression for average shear stress. So average shear stress will be nothing but this shear force divided by total area of this cross section. That is area of two flanges plus area of the web. Okay. So this is average shear stress, and maximum shear stress you can find by, so in this web, at the center of the web, we have y is equal to 0. You put y is equal to 0 here, and you'll get the value of maximum shear stress. And you divide both these two things, and you'll get the ratio. Let me move to the problem 2, and this is total area of the cross section. Total cross section area. That is, you can just simply find out. So that is 2L into T, that is area of web, plus 2 into B into T. So that is the area of two flanges. Now let me move to the problem 2. So in problem 2, now we are going to deal with some composite beams. That is, let's say some part of the beam is, so across the thickness of the beam, there is variation in material. So let's say some part of the thickness of the beam is made of one material, and some part of the thickness of the beam is made of another material. And there can be several variations. But please remember one thing, that in all the composite beams, we assume that the materials are perfectly bonded to each other. Since they are perfectly bonded, so let's say if a pure bending is happening, or let's say only bending is happening, so in all the cases, the strain will not be discontinuous, like the longitudinal strain, or yeah, so the longitudinal strain will not be discontinuous. Okay. And we are dealing with thin beams, transverse strain to yx. In thin beams will be negligible, but in thick beams it will be there. Yeah. So what I'm saying is longitudinal strain is continuous because we assume that, we just write it down. Yeah. So since we assume that the beams are perfectly bonded to each other, so in plane displacements will be continuous across the thickness. So since in plane displacements are continuous across the thickness, and longitudinal strain is del u by del x, let's say, and u is in plane displacement. So, del u by del x will also be continuous across the thickness. Okay, because u is continuous across the thickness. Anyway, so since they are assumed perfectly bonded to each other, so longitudinal strains will be continuous, and but stresses, longitudinal stresses will not be continuous because material is different, Young's modulus will be different. So since longitudinal strains are continuous, longitudinal stresses will not be continuous. Similarly, this transverse shear stress, so that will be continuous, and since transverse shear stress is continuous, your um, transverse shear strain, that will not be continuous because modulus, transverse shear modulus of the material will be different. So these two things you can keep in mind while solving composite material. So in composite material, since they are perfectly bonded, so in plane displacements, in plane means, in case of beam, let's say, a longitudinal displacement, U will be continuous with respect to thickness. Okay? Because the materials are perfectly bonded. So there cannot be discontinuous sliding, right? So, since let's say this is beam and this is U will be in this direction, so there cannot be discontinuous sliding because the materials are perfectly bonded. So from the thickness, U will be continuous. Anyway, and this continuity of transverse shear stress comes from equilibrium equations. So you'll have to derive that, but yeah. So let me write the problem. You have to go for composite beam having rectangular cross section such that one half of the beam, one half of the cross section having square shape is aluminium, and other half, while the other half is steel. When such a beam is bent, such a beam is bent, where will the neutral axis lie? In the cross section. Okay. And that you have to calculate the distance of neutral axis, you have to calculate from the bottom of the cross section. So you have to calculate from the bottom line of cross section. Okay. So let me just draw. So the beam looks something like this. Cross section looks something like this. Say this is aluminium and this is steel, and this height is, let's say, 2h. Then this will be h because each half cross section is square, and this will also be h. Right? So let me do the solution. You have to calculate where will the neutral axis shift, and obviously it's going to shift. It's not going to be at the center, as we will see. So I'm assuming the position of the neutral axis. So let me just do that. So let's say this is center. Let's say this is center. So, and let's say neutral axis is located somewhere here. Let's say it's located somewhere here, and center is located here only. Let's say this is center. So, um, obviously this dimensions I have already written. Let me write again. This is h, and this is 2h only. So let me also write that this is neutral axis. And since neutral axis, then I'm assuming that this is at a distance of a. Let's say this is at distance a from the center, and This is steel. This is aluminum. So now we are here. So I'm just plotting the what I was saying is let U be the displacement of the beam. So let's say this is the beam now. This is some beam. And this is the cross section of the beam. So you can imagine a beam. So along the length of the beam, let's say displacement is U. So that U displacement is going to be continuous because this interface is perfectly bounded here. Okay. So since that is going to be continuous, so U will be function of X, obviously. And it is continuous with respect to Z. So it's not a function of Z, or it will be. Uh, yeah, so it will be function of Z also. So it will just U will be function of Z also. Okay. And it will be Z is actually let me be consistent with the coordinate system, so it will be function of Y also. Y is across the thickness of the beam, and X is across along the length of the beam. So what I'm saying is, since U is continuous with respect to X, with respect to Y, so we have epsilon XX, right? So we have del U by del X, right? Since U is continuous with respect to Y, del U by del X will also be continuous with respect to Y. Because let's say this is Y and U is continuous. Oh, yeah. So that is not necessary. Uh, yeah, this will be continuous because we have only differentiated with respect to X. We have not differentiated with respect to Y. So if U is continuous with respect to Y, so it is not necessary that del U by del Y will also be continuous because it may have continuity like this. So if U vary with Y like this, so at these points, del U by del Y is not continuous. But we are not talking about del U by del Y, we are talking about del U by del X. Okay. So that will be continuous across Y. Anyway, so if I write down the expression for longitudinal strain, so that was minus Y by R for the beam, and it will remain same. Only thing is that the neutral axis, it will be strain will be zero. So let's say it will start from here and go like this. It will next on here and it is continuous. You can see that it is continuous because the material is perfectly bonded. So this is the plot of epsilon xx and it is minus Y by R. Okay. And then let's plot sigma xx. So we use a different color. Since this is a uniaction case, so sigma xx will be zero here. And it will start from some positive quantity. So sigma xx will be E into epsilon xx. So since epsilon xx is positive here, sigma xx will also be positive. So it will, and that will be E of steel here. So let's say start from here and then it goes like this. So So it goes like the way. Now here, this is in steel. The sigma xx is in steel. So I'm just writing here sigma xx is equal to E of material. I'm writing EM. Maybe steel or aluminum, anything can be there. And EM times epsilon xx, right? So here it will be discontinuous because your strain is continuous, but your modulus is discontinuous. So here there will be sudden change in modulus. So E into epsilon xx, here there will be discontinuity. So it will be something like this. So let's say here it has some value, and here there will be some discontinuity. This purple one is in aluminium, but here there is a discontinuity at the interface. Discontinuity of longitudinal stress. Anyway, so let me just find out the position of neutral axis. So I'm saying that y is distance from neutral axis, and at the position where material changes, bending stress profile will also change. Okay? So we can say that the sigma xx will be E times epsilon xx, which is given by, and let's say, yeah, so which is given by sigma xx in steel. If I write sigma xx in steel, so its expression will be minus of Young's modulus of steel into y by r, because epsilon xx is y by r. And this will be valid for y going from, so steel ranges from, the y is now from neutral axis. So y is, let's say, any point here from the neutral axis. Anyway, so y will go from, for the steel, y will go from minus h by 2. So since we are measuring from neutral axis, so this distance is nothing but, I'm writing distance, so this will be h minus a, right? Yeah. So start from minus of h minus a, and we'll go up to y is equal to 8, right? So this is steel. And then if we write in aluminium, so that will be minus of EA into y by r. And this is valid for the reason we are starting from y is equal to a and going up to a plus h, a plus h, right? So because this distance is h, so this total distance will be a plus h. This is a, and this I will already written. This is h minus. Okay, so let me write, and since it is a case of pure bending, so there should not be any axial net resultant axial force. So due to pure bending, total axial force must vanish, in the cross section, and that is Let's find more like actual force about on neutral axis. I mean, it will not be about neutral axis, but it will be total actual force in the cross section. So that will be actual force in steel plus actual force in aluminium. So that will be sigma xx in steel dA plus area of aluminium sigma xx in aluminium times dA, and that should be zero. Right? So total actual force should be zero because it is a case of pure bending, and this will lead to let's put the expression for sigma xx s and sigma xx a. We put es by r, and you're going from minus of h minus a to a, and here you have y dy. I'm assuming that I have the unit width of the beam. The width is unit. That's why I've taken one. Dz is one. Okay. I mean integral of dz is one. So anyway, so and this is going from a to, and this will be minus of ea by r. And this will go from a to h plus 8 and y dy, so that will go to 0. So if you now try to solve this, so here you get y square by 2. So it means you get a square minus h minus a square, right? And I'm taking this plus of ea by er here, ea by es t, and here also you get h plus a to the whole square minus a square. And you have to find the value of a in terms of h. So if you solve this, so finally you will get um, minus of h square 1 minus ea by es plus 2ha 1 plus ea by es. You will get this expression if you simplify this. And if you further solve, you will get a is equal to h by 2 es minus ea over es plus e, right? So this will be the final expression. So this is the value of a, and from the bottom of the beam, the distance of neutral axis will be h minus a. So we can say that the position of neutral axis from bottom line of cross section is h minus h by 2 es minus e or es plus e. This will be the final expression. Now let me go to problem 3. So problem 3 is a beam of composite cross section again. This is problem of composite cross section. So again, you have to remember longitudinal strain is going to be continuous because material interfaces are perfectly bounded to each other. The beam of composite cross section is subjected to bending moment mz is equal to 30 kilometer. And what you have to find, first part, the curvature induced in the beam. In the second part, you have to find maximum bending stress in wood, because that one material will be wood maximum bending stress in wood. I'll draw the diagram this way. Third part, you have to find maximum bending stress in steel. The second material is steel. So diagram for the section is like this. Um, let's say at the sides there is steel. So this is steel. Okay. So and at the center you have wood. Not exactly at the center. So here you have wood. And all the interfaces are perfectly bonded to each other. And at the center you have empty space. So and the coordinate system is this is y and this is z. So let me just write it down. Dimensions. Dimensions is um this is 60 mm. This is 90 mm. This is also 60 mm. And here this dimension is 6 mm. This is also 6 mm. And here you have middle part. So that is 120 mm. And this is steel. Yes is equal to 200 GPa. And this is wood. So here we have wood. And its material property is EW, which is 10 GPa. Right? This is 10 GPa, gigapascal. And here at the center you have void, which is empty space. This will not have any modulus. So what do you think? So let me so how will you find the curvature first? So you know that. So you have learned the formula m by I is equal to E by R. E into curvature is equal to m by I. So m will be EI into curvature. So curvature will be m by EL. So m you already have, E you already have, EI you do not have. EI is the something known as bending stiffness that you need to find of this whole cross section. So what do you think? So shall we add the bending stiffness of these two material, or shall we, are they in series or parallel? So if they will be in parallel, the second material will contribute in reducing the, I mean, and I'm just saying because. Yeah. What I want to say is, shall we add the bending stiffnesses of these two materials, or shall we just do reciprocal of them and then add, like we do in something known as parallel resistance or series resistance? So if you are able to imagine, so this steel, if we only have wood, and if we try to bend it, okay, so this cross section will be bent like this. So if we try to bend this, so there will be less resistance. And if we have steel inserted in it, so resistance will increase. It means we should add the stiffnesses of both the materials. Because if we do not have steel, or let's say only if we have steel, so resistance will be less compared to bending resistance will be less uh, compared to when we have steel plus wood. So these bending stiffness of these two materials should get added, right? It means the stiffnesses are in parallel, right? Because when the stiffnesses are in parallel, you add them. When stiffnesses are in series, say you have spring in series, you do reciprocal of them in the when that effect will get reduced. But in series, that effect get enhanced. Anyway, so solution. Firstly, you'll have to find bending stiffness of cross section. So bending stiffness of the cross section, right? What that will be. So EI total. That will be EI steel plus EI wood. And EI steel, what will be that? So that will be twice of, because there are two steels, twice of E steel times I will be 1 by 12, and B is how much? Um, Width is 6 mm and it's cube. So that will be 210, right? 210 to the whole cube. So that will be the EI for steel plus EI for wood. So let's say EW for wood is, knowledge for wood is EW, and then for finding, so for finding the second moment of area, so you find total second moment of area and then subtract the second moment of area of this body. Okay. So that will be total second moment of area for this central part will be 1 by 12, which is 120. And H is again 210 to the whole cube, right? And minus 1 by 12, which is again 120. And now thickness is 90. Okay. So if you solve this, so finally we'll get, let me just solve it. So EW will have to put in megapascal, EW and ES, because dimensions you have put in mm. So megapascal is Newton per mm square. So the final answer will be Newton mm square, because I is mm to the power 4. So finally, what you will get, so you can calculate, not calculating. Finally, you will have the value of EI total. Once you have the value of EI total, so that will be Newton mm square. Once you have the value of EI total, so you can calculate the curvature. The curvature induced is first part. curvature induced in the beam. So that will be nothing but kappa. So that means mz by ei total. So you have ei total, you have mz, you can just find out the value. Okay. Now you have to find maximum bending stress in steel, maximum bending stress in steel, and maximum bending stress in wood. So how will you do it? So you can easily find out because you have the expression of ei total, you have the expression. Mz is given in the question. Just be consistent with units. Okay. So a curvature has the units of mm because it is 1 over r. R is in mm. So yeah, curvature will have units of mm inverse because it is 1 over r. Anyway, so maximum bending stress you want to find out. In steel. So how will you find it out? So as I told you that the longitudinal strain does not changes in steel. In the material, longitudinal strain is continuous. Only the stress will be discontinuous. So you just need to find out the value of strain at which stress is maximum. And you have the modulus and you can easily find out stress. So find out value of strain. So you know that stress is what is the expression for stress? So that is E into epsilon, which is minus y by r, right? And 1 by r is curvature, so you have minus E into y into kappa, right? So maximum will be at how much? So y is at the center, so maximum will be at y equal to minus h by 2 is total height is h. It will be at 105, right? So 60 plus 45, so it will be minus 105. You type in mm. Anyway, so this is the this is a kind of strain. So you already have strain. Strain is maximum strain is and this will be plus because I'm taking at y is equal to minus 105. So kappa we already have, so I'm just writing here kappa. And y will be I'm writing in mm, so it will be 0.045 plus 0.06. I'm writing in meter now. So you'll have to insert this in Newton per meter square. And kappa also you have to insert this in 1 over meter, right? Because so you have to be consistent in units. So this you already know. You found out in part A, right? And this is already known to you, which is let's say steel. This is given, right? Will be given in the question if it is not given here. So you can easily find it out. Similarly, third part maximum bending stress in wood. We'll try to find it out. So similarly, it will be sigma wood, and this will be minus of wood, E of wood times y at minus h by 2. So minus minus will be plus. Kappa will remain as it is, then h by 2 is 0.045 plus 0.06. And this will be Newton per meter square. This will also be okay. Yeah, you can ask me if you have any doubt. Okay, so if you do not have any doubt, we'll stop here for today and we will meet in the next week. Thank you for your attention.